Today's webinar on digital twins and structural health monitoring data integration is presented by Professor Amir Ali Najafi from Texas A&M University in the US. This webinar follows our well-attended May 14th webinar on recent advancements in SHM for tunnels, which was presented by Professor Werner Leinhardt from Graz University of Technology in Austria. In today's webinar, Professor Najafi's presentation will highlight the vital role of SHM data in creating a reliable digital twin for infrastructure systems. As you all know, digital twins enable real-time monitoring, predictive maintenance, and informed decision making. Digital twins and proper application of digital twins enhance resilience, reduce costs, and extend asset life through accurate data-driven insights into performance, usage, and potential failure risks. Before I introduce our webinar presenter, a few words about the Society for CSHM, for those of you who may not be familiar with its mission and activities. The goal and the mission of the SCSHM essentially is to enable practitioners, academics, and research community in advancement of structural health monitoring as an effective tool in asset management. CSHM is a global organization of civil structural health monitoring practitioners and researchers. Members include practitioners, scientists, students, academics, engineers working in the field, government and regional authorities, and infrastructure managers. The board include members from academia, from professional organizations, and industry. These are the current executive committee members for SCSHM. Committees include Young Members Committee. Our presenter today is one of the founders of the Young Members Committee, Data Enhanced Infrastructure Engineering and Standardization. I would say the Society's hallmark contribution to the field is its esteemed publication, the Journal of Civil Structural Health Monitoring, which is widely respected in the profession and led by Chief Editor Professor Farhad Ansari of University of Illinois in Chicago. The official events include conferences, workshops, seminars, and webinars. Today as I mentioned, is our second webinar for this year. And pre-conference short courses which have been widely received by the community. These are some of the past and upcoming conferences of Society's conferences. The next one will be which is the 13th International Conference on Structural Health Monitoring of Intelligent Infrastructure, will be held in Graz, Austria, September 1 to 5. We look forward to see as many of you as possible. Today's presenter is, as I mentioned, Professor Amir Ali Najafi. A brief introduction for him. He's an assistant professor in the Zachary Department of Civil and Environmental Engineering at Texas A&M University. His research focuses on bridge engineering, structural health monitoring, large-scale testing, non-destructive evaluation, and structural controls. He has led or contributed to major infrastructure projects, including FHWA, or Federal Highway Administration's Long-Term Bridge Performance Program, New Jersey DOT's Bridge Resource Program, New Jersey Transit's Digital Twin Modeling of Railway Bridges, and New York, New Jersey Port Authority's asset management efforts for the George Washington Bridge. He also supports the US DOT's Advanced Bridge Technology Clearinghouse project. He has led large-scale testing programs at Rutgers University's Bridge Evaluation and Accelerated Structural Testing Facility, examining the impact of extreme environmental and traffic loading on bridges. And he has conducted seismic testing of curved bridges at University of Illinois in Urbana-Champaign. He recently received Texas Department of Transportation's funding to investigate mitigation strategies for blast and fire damage in bridges. He is active in TRB, SCSHM, EMI, and serves on the editorial boards of Frontiers in Built Environment and the Journal of Civil Structural Health Monitoring. With that introduction, I would like to invite Professor Najafi to start his presentation.
Thank you. Just going to share my screen now.
Okay.
Okay, so I assume it's coming through now.
Yes.
All right, well, thank you very much. Thank you, Dr. Maher. Howdy, ladies and gentlemen. My name is Amir Ali Najafi. As Dr. Maher kindly introduced, I am an assistant professor in the Zachary Department of Civil and Environmental Engineering here at Texas A&M. The topic of today's discussion is digital twins, looking at integration of structural health monitoring data. In addition to integration, something I'll be talking about quite a bit is generation of structural health monitoring data. Digital twins give us the valuable capability of also being able to generate data. So that's something I'll talk about. Let's see how this works. There it is. Just a little snippet about me. I lead the Built Environment Analysis and Modeling Laboratory at Texas A&M. My research interests are resilient infrastructure under natural and human-caused hazards. I'm mostly concerned with flooding and fire, advanced bridge systems and technologies, railway engineering, both on the freight and transit side, structural monitoring and control systems, and discrete event simulation for more of those network-level type analyses and systems. So just briefly, the outline of today's presentation, we'll talk about motivation and goals leading us to digital twins, an introduction to digital twins. We're going to talk about integration of visual information and IoT sensors. We'll talk about the particular application area of scenario simulation, and then we shall wrap up. All right. Let's get started. Much of what I'll describe in this presentation in terms of examples has to do with bridges. The concepts generally apply to all of built infrastructure, but bridges are just very just prime examples of civil infrastructure, and they are very relatable. So that's why you will see a lot of bridge talk. So let's get started. In the United States, the Federal Highway Administration mandates that we inspect bridges every 24 months. Now, depending on the condition and status of the bridge, meaning things like the bridge type, condition, associated risks, this frequency can be changed up a little bit. But even with this frequency, you can sort of tell that critical damages can be missed. So if there is a damage, there can be many months before someone looks at it. A prime example of this is the I-40 Hernando de Soto Bridge between the states of Arkansas and Tennessee, where in 2021, a major fracture was found. It was caused by hydrogen-induced cracking during the welding and fabrication process. And then it was realized that through many routine monitoring sessions that this crack had actually been missed. The crack existed, it had gradually propagated, it was missed. It was only through amateur drone footage that people discovered later on that the crack was actually there and slowly propagating. So really, this goes to show you two things. One, inspections are done by human beings. They are prone to errors. And number two, there is a huge interval over which the bridge is not being inspected. And that can be a problem. Furthermore, what happens is once bridge inspection is performed, the data is generally shared on a publicly accessible website. It's called Info Bridges that Federal Highway Administration has. This website hosts information pertaining to the National Bridge Inventory and the National Bridge Elements. So these are key data like bridge location, materials, span length, traffic volume, and the inspection ratings provided by the inspectors. As you can tell, while this information is very useful, we definitely need it, it's only a snapshot of the actual data that we might need to make proper assertions about a bridge's health. So really, this is where newer technologies like digital twins can come in. We can have advanced structural health monitoring, computer vision, IoT sensors, all those things coming in to really help us out. There are also modern inspection techniques that exist, as many of you are well aware. We can, for example, for those that may be sort of new to the topic, we might have UAV inspection being deployed. UAVs are great for those hard to reach areas. We might have LiDAR for getting precision measurements. We might have a variety of sensors, accelerometers, strain gauges, et cetera, being utilized. And we might, just put up a ladder, get up close and inspect it. So really, modern inspections are also out there. They're not really typically required by federal mandates or even state mandates, but some asset owners choose to deploy them. So it's really up to their choice. But having said that, modern inspections are also subject to limitations, and I'll talk about what these limitations are next. So let's say there's some sort of a natural disaster, earthquake of sorts, and you are trying to perform post-event inspection. Well, the issue that modern inspection approaches have is that damages are often localized and hard to detect, and we currently don't really have a test bed for performing modern inspections. So once you arrive at the site and you're trying to perform your inspection, you don't really know where to start. And your drone might have a finite battery life. You might have a finite amount of time. How do you go about navigating your inspection process, right? The other issue we might have is if you see damage, and let's say your computer vision techniques are able to pick up the damage and really identify what the issues are, how do you translate those localized damages to global behavior? So if you see spalling and rebar exposure, how do you convert that to the global stability of the entire structure? We really don't have answers to these types of questions. So that's really one part of the challenge. The second part has to do with routine monitoring. Whenever we perform routine monitoring, we're comparing the current status and behavior to some sort of a benchmark. And the truth is, we don't really have a ground truth to work off of in many instances. So when you're comparing today's behavior to the past, if you don't have the past, you can't really make assertions as to what's going on to the health of the structure. In addition, if we are deploying all kinds of sensors and fancy equipment, they have calibration, they have noise issues. Those are all things we need to think about. And then it's also the issue of the response interpretation that we really don't have answers to. Okay, so hopefully this is where digital twins come in and they can fill in those gaps and provide us with platforms to work off of, additional data sets to work with, and really they are able to augment existing modern approaches. So a digital twin environment is, and I'm going to sort of start out with a definition of what a digital twin is and a digital twin framework is. A digital twin environment is one that has multiple constituents. The first is the physical part. It includes a single system that might be a bridge. It can also be a complex systems or series of complex systems, including like an urban network. It will include a digital twin. Usually it's going to be built out of a three-dimensional graphical model. It's going to have physics-based capabilities. It's going to have heuristic-based capabilities. I'll talk more about these in a couple minutes. To connect the physical twin to the digital twin, we're going to have connection devices. These are your UAVs, cameras, LiDAR, IoT sensors. And to connect the digital twin to the physical twin, we're going to have services. Those are essentially the benefits that the digital twin provides to the physical asset. So these include scenario simulation, lifecycle management, rapid sensing and model updating, damage detection. This list isn't meant to be exhaustive. I'm sure Some of you may be working on areas that are also services that can be considered services. However, these are just a couple that I thought of that are fairly useful on a day-to-day basis. So this is really what a digital twin environment looks like. Before this session, I did a quick keyword-based search on Web of Science, looking at terms like digital twin, bridges, buildings, civil engineering, infrastructure, and developed this cluster term map. Most of what I found is the literature is currently focused on SHM quite a bit, as can be shown in the green. In the red, there's a lot of work being done in construction, advanced or accelerated construction. There's also some more preliminary mathematical algorithmic work being done on photogrammetry, various aspects of digital twinning. So overall, it's a very hot topic. It's continuing to grow. Citations are on the rise. I found over 800 publications between 1990 and 2025. So just wanted to list this out there. And then the next question that's often asked is, so what is the difference between a BIM model and a digital twin? Well, a BIM model and digital twin are closely linked, but they differ in scope and functionality. That's how I would describe it. BIM tends to be more static in terms of its representation. So we have information that we capture like shape, structure, materials, hierarchy of construction. Those are things that are generally described in a BIM. BIM is widely used in design. It's widely used in construction. But a digital twin, in contrast, will be a little bit different. It will extend these concepts by incorporating a variety of different data, often real-time data. It will enable behavioral, temporal tracking of the asset's behaviors. It will have predictive modeling capabilities. It will have some sort of a continuous feedback mechanism to help the actual physical twin asset. So that's really how I would describe it. BIM tends to be more static. Digital twin tends to be more dynamic. And there are a lot of elements that can be added in between, and there's an abundance of literature talking about all these various components. So if we take BIM and add structural analysis capabilities to it, that's one part of it. We can add AI to it. We can add IoT sensors to it. We can also get really fancy with visualization. We can talk about mixed reality, augmented reality, virtual reality, and then there's also the feedback component that I talked about, and all those interactions with the real world that the digital twin will offer. So it's basically BIM with a lot more capabilities. Okay, so let's talk about an integration of structural health monitoring data. First, I'll talk about visual information. Then I will get into IoT sensors and basically time series. So when it comes to visual information, capture and reconstruction of three-dimensional data is really the first and the fundamental step for integrating the visual information. There are a variety of sensors out there. You have your thermal cameras, your LiDARs, your RGB cameras. They could be placed on pedestals, tripods. They can be placed on mounted on UAVs for those hard to reach areas. But once you have your visual information, your camera footage, then we typically like to perform photogrammetry. For those that are new to the area, photogrammetry is based on the science of epipolar geometry and this concept of essential matrix. So once we have a camera and we take a snapshot of an object and we move it in space, we generally identify this matrix called an essential matrix, which we decompose into camera rotation and translation. Once we do this, then between our images, we have to perform feature matching, finding features that are identical. And then we perform triangulation, which is deciphering where a point is in three-dimensional space. So that's what photogrammetry is. And the end product of a photogrammetry algorithm, such as structure from motion or multi-view stereo, are point clouds. Point clouds are essentially much of, or the end product of a three-dimensional data capture. We can also perform this using LiDAR. LiDAR is just shooting laser impulses at really high frequencies. So here is an example of photogrammetry being performed on this reinforced concrete structure. This is actually a fire watch tower in Staten Island, New York. That's where I used to live, and this was one of my little side projects. So we fly our UAV, which is shown here in the little speck next to the actual building. We fly it around, getting really good shots from all different angles. We perform feature matching between all our images, and then we develop the point cloud. And this is all done through commercial software, so there's very little I have to do as an engineer. I pretty much just let the software take over. The issue that point clouds have when you are developing a digital twin is that point clouds lack topological structure, and they require significant memory and computational demands. What I mean by lack of topological structure is you cannot infer planes, curves, object boundaries from an actual point cloud in an algorithmic sense. So all that a point cloud is a list of X, Y, Z coordinates and RGB colors. There is no relation between the points. So that's really a flaw when it comes to like doing more advanced computational work. So generally speaking, what we like to do is as soon as we have a point cloud, we like to take it, segment it into meaningful components, like bridge deck, like piers, railings, so forth. There are a variety of different means for performing this. We have geometric segmentation. We have semantic segmentation, where we use deep learning to classify the various components, and we need to have some sort of a pre-trained model to help us out. We can perform instance segmentation. This is when you detect individual objects that have the same class. We have supervoxel, graph-based, color-based segmentation. These are all available. The two segmentation approaches that are used the most are semantic and instance. Okay, so that's the second step. Once we have our point cloud segmented, then we address the flaw that a point cloud has in creating a structured representation. So we take the raw point cloud and convert it, transform it into a structured format through different algorithms. One of these algorithms is creating three-dimensional mesh. So you take any 3 points and you create a plane in between them, like a triangle. 3D meshes are great for ideal visualization and inspection techniques. So this is like the most basic approach. We can also use voxel grids. Voxel grids basically divide the three-dimensional space into cubes, sort of like what a pixel is to the plane. A voxel is a volumetric pixel for three-dimensional volume. So these are useful for any sort of volume-based analysis. We also have surface models, including the likes of NURBS, B-splines. These are useful for CAD-ready geometry, for more advanced type of engineering work, manufacturing, simulation, things like that. They are definitely on the more advanced side of things, and they create a lot smoother surfaces than, for example, 3D meshes. So by doing this, we are now representing our data in a much more structured manner. We are reducing data redundancy, and we're making the computation a lot more efficient. Now, there are a lot of commercial software out there that can perform scan to beam. So they can take your point cloud and they can convert it directly into a BIM file. But again, these are commercial. They have their own successes, their own flaws. But generally, they follow multiple steps. First, you have your scanning. Then you have your classification, extraction of various important parts, like planes, volumes, spaces, gaps. There's a lot of refining that's done, removing erroneous points. And finally, we fit geometric primitives to the various surfaces and create our BIM model. What's often added to a lot of these scan to BIM approaches is also the capability to create IFC datasets. So what that means is you can make your BIM model a lot more parametric. So you can have those geometric, semantic, all those relationships encoded into your three-dimensional model. So this is a capability that's also very useful. Now, in many instances, we want to get even fancier. We want to perform three-dimensional immersive integration, putting our digital twin on those mixed reality, virtual reality, augmented reality headsets, right? And this is fine. Many people like to do this for research purposes or for practical purposes. 3D immersive integration has multiple steps. First, we build our digital twin, like our BIM model. and we import it into a graphical environment like many of the gaming environments that exist out there, like Unity. Within this environment, we place virtual sensors and link them to the actual IoT data streams that come from the actual asset. Then we create our augmented reality application. So if you're like dealing with Unity, there are toolkits that are out there, MRTK, Vuforia. These are basically tools that make your mixed reality have a lot of different capabilities that you can interact with. It's like interactive buttons or other features. The next step is we deploy the application onto mixed reality headsets. Companies are out there that offer these headsets, like Microsoft may have HoloLens, Apple has its own product. Everyone is now sort of targeting this mixed reality domain. And then you perform your monitoring as the final step. So we align the virtual model with the actual real bridge. And then you can actually, like within this environment, you can like tap sensors and live stream data. You can see it on your headset, or you can receive alerts. You know, we can create thresholds so that when a vibration level is reached, you can get some sort of an alert. So this is a capability that's also valuable. Here's an example of Minnesota Department of Transportation, one of the first in the United States deploying digital twin technology. They actually have a really interesting document that's publicly accessible online on this. But basically what they did was they used a UAV to assist with their inspection process. They performed photogrammetry, developed this digital twin workflow, and they concluded that with this approach, they can cut inspection hours by 30%, they can reduce fuel time, they can reduce traffic disruptions, and also improve safety and reduce risks. Their approach was also augmented with AI-powered defect detection. So things like cracking, spalling were detected using AI and machine learning for pretty much streamlining the inspection process, making it a lot faster and accurate. Another thing that's often of interest, especially to many DOTs, is this concept of high-performance web-based visualization. It's basically trying to visualize sensor and model data in real time on a web-based platform, which is useful. It could inform authorities, engineers, inspectors. What I've done on this website, on this slide is I have posted some of the tools that are necessary, that are useful. Some examples include, for example, JavaScript, WebGL. These are basically tools that handle and render three-dimensional graphics directly on a browser. We have WebAssembly, which is used to boost those offload heavy computations that you need for like physics-based modeling. So all those matrix operations and so forth. We have TensorFlow.js. It enables in-browser deep learning using GPU acceleration. We have 3.js. It simplifies all those 3D scenes, including lighting, geometry, animation. We have a variety of culling techniques that exist to improve speed by basically not rendering when something is hidden or when it's out of view. We have WebSocket and MQTT, which allow streaming of data from live sensors onto the visualization dashboard. So altogether, these things give us real-time capabilities. They are browser-based, and they provide us with high-fidelity visualization for all the SHM data. Here is an example of this. Norway is a country that generally has excellent infrastructure, but they had this 80-year-old Stava bridge that was long a source of stress for many of these Norwegian public road administration officials. So what they did was they developed a digital twin. They instrumented the bridge with structural health monitoring sensors and just basically left it at that. What happened in the year 2021 was there was a serious structural flaw found in one of the components of this bridge that notified the inspectors to come out, and they did. They were deployed. They were able to confirm the deficiency, which led to the full closure of the bridge. And they had to basically build an interim bridge temporarily until a final bridge was built many months later. So this shows you pretty much some of the capabilities that digital twinning offers in in serving like practical purposes, like and improving safety. Finally, I did mention IFC classes. I just want to talk a little bit more. So industry foundation classes are basically an open data format standard that's designed for a lot of various infrastructure assets out there, buildings, bridges, other assets that are out there. They are a way of representing digital assets, and they are interoperable. What that means is you can work with IFC models within different software classes or software types. So here is the pipeline for an industry foundation class. You basically have to follow through all these steps: data acquisition, pre-processing, segmentation, 3D surface modeling, and finally, you generate your IFC model. And then, of course, we have a whole bunch of software out there that are IFC capable. We have Revit, Bentley, Diana, FEA. These are all software that are out there that have full or at least partial IFC capabilities that we can work with. So here's what an IFC schema might, for example, look like. We have a whole bunch of categories such as geometry, materials, components, defects, other metadata. We have IFC classes, like all their constituents, their components, and each one has a purpose and a description that's generally filled in. Okay, so that's enough about the visual information. Now we talk about those hardwired or wireless IoT sensors. And their corresponding integration. When it comes to data collection, there are generally two things we're concerned with in research and on the practicing side. These are coverage and fidelity. Coverage is looking at all the various scenarios that exist and how we can take all our parameters and perturb them to see all the possible outcomes, and then we can make informed decisions. Fidelity is a little bit different. It's pretty much concerned with accuracy and precision of data. So when it comes to computational research and simulations, you can get a lot of coverage, right? You can run the simulation 1,000 times. You can get all kinds of possible outcomes. When it comes to field work and basically laboratory testing and instrumentation with IoT sensors, they tend to be better with fidelity. And they tend to be on the shorter end of coverage, simply because running tests and getting deployed to field is expensive. We can't be doing this all the time. So with a lot of the digital twin literature out there, what I've read is they try to bridge this gap that exists between simulation and testing. So you can have both good coverage and a high fidelity data sets. So the way IoT implementation works is you obviously have your IoT sensors, strain gauges, tilt meters, accelerometers, load cells, all the things that generate your time series and tabular data. Those can be triggered manually or in an automated manner. You can then pre-process them. You can have your local servers. You can have your fog layer, which is like your edge device or like your low latency sensors. And then we can have cloud computing. These are all things that basically filter your data sets, compress your data sets, crop, align, synchronize your data sets. Then the next thing we like to do is it's data transfer and storage. So obviously you can have your local servers, you can have on-cloud computing, and there's various classes of on-cloud computing, like infrastructure as a service. This is when we provide access to like resources like virtual machines, virtual storage. We can have platform as a service. This is when we provide runtime environments, development, deployment tool applications. Software as a service. This is when we provide software as a service to the end user. So these are pretty much the different types of on-cloud computing that exist. And also, whenever you are transferring data from multiple devices, you also have to consider air interface design. So some of the methodologies are listed here, but essentially you can transfer information over different frequency bandwidths. You can transfer information with different amplitudes. There are time slicing methods. There are unique code-based access methods. These are all the various methods that exist. Each have their own benefits and issues. And finally, we performed like the classic system identification and model integration, right? All those autoregressive methods, the eigenvalue realization algorithms, the stochastic subspace identification, modal identification, transfer function fitting algorithms, all those things. So most of what you're seeing here is classic SHM. We've been doing it for a while. For the digital twin side, it's a little bit different. We generally have the physical asset with sensors deployed on it, and then we have the digital twin, which works in the following way. Generally speaking, we develop a document-based finite element model of the structure. From all those IoT vibrational data, we update the parameters of the finite element model, and we generate this updated FE model. If we are also lucky enough to be doing laboratory testing, then we have access to force data, excitation data, any sort of input that's coming in. We use those to get an even higher quality and updated finite element model. And then once you have your digital twin, then you can simulate the digital twin's response in parallel with the physical twin's response. And you are basically, you're now blessed with a tool that's giving you a continuous stream of forecasting, decision-making capabilities. And this is really how SHM for digital twin will be different than like classical SHM. So we have this continuous integration of real time. It's supporting future predictions. It's improving life cycle management. And you sort of think about it as a feedback loop where the digital twin keeps getting updated and it keeps providing us with a continuous stream of data. Now, going back to some of the slides I presented before, rapid visualization and capabilities are also important, right? We want to have fast-running digital twins for making rapid decisions or for many different applications. This is where things like surrogate models come in. Surrogate models, for those that are not super into this domain, are basically simplified models and fast-running approximations of more complex simulations. So instead of running full-on finite element, we have surrogate alternatives. The way they work is we perform our data collection from anything from low fidelity data sets, high fidelity simulated experimental data sets. Then we choose our model type. So common options are generally radial basis functions, support vector regression, even neural networks, deep learning. These are all possible choices when it comes to surrogate modeling. We can have a single layer of a surrogate model. We call those single fidelity. We can also have multi-fidelity models where you take multiple of these models, concatenate them together for better capabilities. And finally, we have to perform optimization, validation, calibration. That's where the challenge really comes in. So surrogate modeling is a fundamental constituent of a lot of the digital twin literature that's out there. And here's an example. Here we have this very simple cantilever setup. We have our visualization in the back. On this cantilever, we have several strain gauges. And there's a surrogate model being ran in the background. And you can kind of see like the fast physics-based simulation and visualization running simultaneous with the actual exertion of forces on the specimen. Okay, so now I want to talk about the particular application area of scenario simulation, which is going to be very useful for generating data. And data generation is like a big part of engineering and research nowadays. Okay, so scenario simulation allows us to test how infrastructure behaves under different conditions before issues arise, or we can have them run in parallel so that when issues arise, we can have all these scenarios listed in front of us that we can choose and learn from, right? We can find possible sources of damage and so forth. One of the types of scenario simulation that we've worked on in the past has been this idea of structural safety scenarios. So we model things like bearing settlement, crack propagation to assess how loads might redistribute, and for potential failure mode analysis. We can also perform retrofit scenarios. So we can look at different alternative scenarios of retrofitting, like in railway bridges, you might be looking at these customized timber ties, which you can like quickly vary in your digital twin environment in terms of their rotation and like positioning and dimensions in order to find geometry and alignment that works best for the railway track. Another example might be environmental and hazard scenarios. So we might use a digital twin environment to visualize accelerated or to visualize deterioration in an accelerated manner. So you can have like corrosion forecasting that could be useful for like for demonstrating something to a decision maker. And we can also simulate like flooding, wind, and how they impact the asset to support more on the risk mitigation side of things. So digital twins can be used for predictive maintenance and those resilience planning types of engineering works. We can also, when it comes to research and engineering practice, we're also oftentimes concerned with a lack of data sets. Nowadays, we're all talking about AI, machine learning. One of the concerns we have is we don't have enough data sets. So we can actually develop a digital twin that provides us with synthetic databases. So we can develop structural models with physics-based damage being simulated, like cracking, spalling, and then we can generate like photorealistic visualizations of what damage might look like under different scenarios. We can also use the digital twin for pre-inspection and planning. So let's say you are someone who has a UAV and wants to go out and perform actual inspection. You can use the digital twin environment to optimize the path planning before your actual deployment. It saves you time, it saves you battery life when you're out there, and improves the quality of your data set. So you can find out what is the best path that gives you the best coverage quality when it comes to your points, your point clouds. And also within digital twin environment, don't forget, you can change and check a lot of different environmental conditions, lighting, cloudy days, all those things. Now, I keep talking about visualization and graphics. There are a lot of open source tools that are out there that actually help us in developing our digital twin. One of the tools that we used was Blender. Blender is an open source software. It helps translate a lot of those engineering models into like visual interactive environments. Blender is actually developed for Hollywood level animations. So a lot of people have used Blender to make animations that maybe we've seen on movie screens, right? But we can also use it for digital twinning because the benefit of Blender is it has a Python API. It can be automated in streaming a lot of the live data streams that come through from IoT sensors. And it can work with simulation outputs from other tools like some of the finite element software that exists. There are also other open source platforms that are out there. I've listed them here for those that are interested. Paraview, Open Modelica, QGIS. I'm a supporter of open source publication and software, so I just wanted to share this with the audience here. Okay, so then we arrive at this graphics-based digital twin framework where we basically start with our as-built structure. This is your physical twin. From this, we develop our finite element model. We use the finite element model mesh to help develop our computer graphics model. From the finite element model, we can also simulate structural responses. This is mostly your linear elastic response. We can also have plastic behavior, those damage modeling approaches that exist. And then these responses are then used to visualize the computer graphics. The benefit of a graphics-based digital twin environment is it sort of serves as a synthetic replica of the as-built environment. It combines high-fidelity modeling to generate photorealistic renderings, and it could support SHM in a lot of different ways. So obviously, some of the functions are that I've talked about before: synthetic data generation, automatic labeling, using them for UAV inspection path planning, visualization of localized damages. We can also test a variety of different computer vision-based strategies, simulating those environmental conditions such as lighting, all those things, and basically helping interpret some of the responses we see from actual SHM we perform out in the real world. So one of the things we did was we said, okay, at the time we were performing this research, we didn't have access to like a physical asset. So we said, let's develop an example benchmark problem involving this 5-story building, and to really test out a lot of the concepts within this benchmark. And I'm not sure if this benchmark is publicly available through like GitHub or some of the other platforms, but I can definitely check for those that are interested. So here we have a 5-story reinforced concrete shear wall building. This is the floor plan, and this is the actual final product of the graphical environment. And basically what we did was to build photorealistic digital twin model, we first had to derive some sort of accurate material texture. So we found pictures of stucco on Google. And then within our Blender environment, we were able to create various textures, a normal map, a roughness map, displacement map. Basically, these are features that describe how light interferes with a surface and make colors and textures very photorealistic. And this is the final product that was generated. And you can kind of see this coloring is being applied to these shear walls on the side of the digital twin model. We also, in parallel, developed our global finite element model in SAP 2000. So here we have slab and shear wall elements being built out of shell elements. We have columns and shear wall edge elements being built out of frame elements. And then information from SAP's Python API is used to update the Blender Python API. So both we can get geometric information, and we can get element types, connectivities, as well as general displacement or modal information can all be shifted into Blender. So once we run the finite element analysis, we identify where damages might be occurring, and we then deploy our physics-based damage model being the more high-fidelity, rigorous finite element analysis. So we zoom in to the component of interest, perform our detailed component level 3D analysis, and we get highly nonlinear analyses like this, like a damage plasticity model showing you where the cracks are. And we can convert this into a photorealistic structural simulation. And I'll show you what this looks like. We start with our damage index map, generate a whole bunch of masks for where different damages might be occurring. Each mask pertains to one kind of damage. So you have cracks, spalling, rebar exposure, et cetera, et cetera. We generate our different textures for that photorealistic component that I talked about, or photorealism that I talked about. And finally, this is our quote-unquote photorealistic structural damage. We don't claim this is like a Hollywood level simulation. However, this is one of like the preliminary works in this domain in trying to use digital twins to augment data sets, right? And you can kind of compare it to what an actual damage might look like following an earthquake. Now, in a lot of instances, we're dealing with non-structural elements, and we don't have like proper material characterization, or we simply don't know what the material is even built out of. So for those types of simulations, excuse me, we are going to perform heuristic-based simulation. So we can look at components like concrete cladding panels, and basically we were able to identify fragility curves within some of the FEMA documents that exist. We fed it our damage parameter from the global finite element model, and then derived at the expected amount of damage, and then converted that to the photorealistic image. So here's an example of our heuristic-based damage representation. On the left, you're seeing the simulation. On the right, you're seeing an actual post-earthquake damage. And then finally, we put all of this benchmark problem together for a seismic application. So again, we have our virtual twin. It has the finite element components. It has the computer graphics model. We give it a whole bunch of earthquakes. Within this environment, we have physics-based simulation. We have heuristic-based simulation. And we can see the response to earthquake 1. I'm just going to show you some of the cracking because I don't know if the resolution is good on this image. You can kind of see some of it here. Here's the shear wall where the cracking is appearing. Again, a lot of this is based on the physics-based model. A lot of it is based on the heuristic-based. Some cracking here and more cracking on the shear wall. And finally, I think this might have been the most high intensity. You can kind of see a lot more. So again, anytime we are dealing with an environment with a situation where you are lacking data set, digital twins can be used for augmenting your existing data sets, right? And this is exactly one of the ways. So this procedure was constructed just to demonstrate the graphics-based digital twin and its capabilities. So here is an actual application that some of my colleagues performed at the University of Illinois. So they looked at miter gates, which are pretty much these gates that are built on lock systems in some of the inland waterways we have here in the United States. These gates are pretty much closed to allow water chambers to rise, allowing ships, vessels, barges to travel upstream from a different elevation. Here's what they look like. These miter gates go through a lot of temperature fluctuations, freezing cycles, deterioration, corrosion, everything you can imagine. They're basically exposed to water, they're exposed to a vessel impact. So they take a lot of stress over the course of 50, 70, 80-year lifespans that they have. And most of them are in pretty late stage or old age condition. Some of the load cases that they experience repeatedly is the environmental one. So it has to do with some of the hydrostatic load that exists. In load case 1, we have the gates being open. So the downstream and upstream are basically similar in terms of hydrostatic pressure profile. In load case 2, you have the gate closed. So upstream might fill up and downstream is still empty. So you're going to get a final product that looks like this in terms of pressure profile. So it's this constant switching between load case 1 and 2 that stresses and fatigues the material, right? So what my colleagues did was they decided to perform optical flow displacement monitoring by using cameras instrumented all around these miter gates. And basically what optical flow does is it looks at different brightness patterns between images. And obviously the images you want to compare are between load cases 1 and 2. So here's the digital twin-based model updating that they developed. It starts with this finite element model of these miter gates. There is a photorealistic graphics model that's also generated with all the textures, with all the colors, and pretty much all the realistic lighting conditions. Loading scenarios are applied. We kind of know what loading scenarios are because we can measure the water levels. And then optical flow is used on the field collected images and on the digital twin collected images. And if the simulation does a good job and we are able to capture the behavior out in the real world, our optical flow displacements are going to match. Now, obviously, whenever you have these like complex boundary conditions, loading scenarios, it's really hard to do this. But what the digital twin environment allows you to do is to cycle between all these variations and all these assumptions as to how the boundary conditions might be working, as to how the loading might be behaving. So they were able to do this and to basically find out what the situations were out in the real world when the field images were collected. So here is just some additional images from the perspective, angle of view. You're looking at your rendered image, you're looking at your field collected image. The finite element environment is being shown here. The graphic space model is very good at simulating all the geometric variations from finite element modeling. So if you have an underformed mesh and you deform it in the graphics model, it follows the exact mesh from the finite element. So graphics model is following closely what the finite element does. You can also change environmental conditions. So you have no lighting, you have small lighting changes, and you have large lighting changes. This slide is just showing you some of the surveying that was done, what the chamber walls look like on these miter gates, and results from the optical flow that was performed. I know we're almost out of time. I just want to quickly talk about a few more things. The commercial landscape is fairly narrow when it comes to digital twins. NVIDIA has its Omniverse. They are mostly focused on manufacturing. They serve a whole bunch of companies: Mercedes, Kroger, Schneider Electric, but they have a really interesting array of products or consumers, users that they have posted on their website. I highly recommend those that are interested to check out NVIDIA's Omniverse. Bentley serves much of the civil infrastructure, mostly on the construction side. So they have those 3D, 4D BIM type developments where you can look at the temporal evolution of the construction. Esri, ArcGIS, Reality Digital Twin is mostly for those larger projects, but it also allows indoor-outdoor navigation. In terms of conclusions, the way I see digital twin moving forward, it's going to be used for the full life cycle of assets. It's going to enable 3D as-built modeling, real-time data integration, predictive analytics. So we're going to use it for construction, inspection, maintenance, decommissioning for the full life cycle. It's going to have model-based capabilities, deterioration modeling. So at this point, it's going to be ready for a lot of those practical DOT level applications. And basically, it's going to be the future of bridge management systems. It will have end-to-end capabilities from inventory all the way to lifecycle cost analysis, resource allocation. It's going to have visual dashboards. We talked about real-time updating, condition assessment, maintenance. So it's basically a tool that's going to be really talked about and used quite a bit in the near future. So in conclusion, digital twins are wonderful. They integrate physical infrastructure, SHM data, and analytical models to enable a variety of applications. They allow scenario simulation capabilities for forecasting, structural response, data augmentation, and a lot more. There are many open source platforms that exist. They are harder to work with. However, we can always use the commercial ones that are out there. And now that we have a convergence of IoT simulations and such visualization power, I think it's a good time to move our civil infrastructure capabilities more forward with the capabilities that digital twins offer. These are my references. I thank you for your time and pass it back to you, Ryan. Thank you.
Excellent. Thank you, Amirali, for sharing some of your research and your work on digital twins with us today. Thank you, everyone, for joining us. I know we were just at time. If you do have any questions and you want to stick around for a minute, I think we can do that. Please drop them in the chat. But if not, thank you again for joining us. We will share a recording of today's webinar with you. And please be on the lookout for future events with the Society. Our next webinar, again, is September 17th. And feel free to reach out if you have any questions. So thank you, everyone.